Hello friends, today we will derive rotation matrix about arbitrary point xf and yf. So we will rotate matrix about arbitrary point xf and yf. So this is the object which is to be rotated about this arbitrary point xf and yf. So after rotating this a, b, c, d, I am representing initial as a dash. I am representing initial as a, b, c, d and final figure as a dash, b dash, c dash, d dash. In this, the red one is initial and the blue one is the final. So after rotating this initial figure, I will get this final figure. I am just rotating this figure into this one about arbitrary point xf and yf. So before rotating, first of all I have to bring this point to origin, because rotation is been done with respect to origin. So I will bring this initial figure to origin, because unless and until I will not bring the figure to initial position, that is to origin, then I can't do rotation or I can't perform rotation transformation and I can obtain this figure. So for that I have to bring this figure to the origin. For that I will require translation transformation. So first transformation I will do as translation. So first translation. We will translate point A to origin. For that translating, I will require Tx, that is translation along x direction, and translation along y direction, that is Ty. So Tx and Ty. So I will require the value of Tx and Ty. So since I have to bring this point here, that is origin, so I am moving from right to left, that is I am inching towards negative direction, and here I am moving in downward direction. So for Tx I have to cover minus xf units, and for Ty I have to cover minus yf units. So Tx is minus xf, Ty is minus yf. So standard translation matrix is given as 1 0 0 0 1 0. Tx here is minus xf, so I will write as minus xf. Here Ty is minus yf, so I will write as minus yf. So the matrix will become 1 0 0 0 1 0 minus xf minus yf and 1. So now figure has been brought to origin, means now it will look like, after performing this transformation, the figure will be as shown this figure, that is A, B, C, D. This point A has been brought to origin, so rotation is been done with respect to origin. Now we can perform rotation transformation, because we have to rotate this figure in this way. So second is rotation about origin. So standard rotation matrix is R equal to cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. This is the matrix for rotation transformation. Now the figure will be appeared as, after performing this transformation, that is rotation. This is just for the idea that how the figure will look after performing the transformations. I am representing final figure as A dash, B dash, C dash and D dash. So it will be shown as this way. So this will be the figure after performing rotation, but the rotation is to be done about arbitrary point. So we have to do back translation, that is we have to place this point which was in some arbitrary point. For that I will require translation transformation, so that I will back translate point A having xf and yf, that is arbitrary points xf and yf. So third I will do translation, that is back translation. Third one is translation, back translating point A. So for translation we will require Tx, that is translation along x direction, and we will require Ty, that is translation along y direction. So Tx and Ty we will require. Since we moved close to the origin, that figure was inching close to the origin, so we were having minus direction. So if we are moving away from the origin, that is the figure is moving away from the origin, so we are inching towards positive direction. So along x we were having xf units, so I will write as xf and I will write as yf, right just opposite to which we have done first, that is translation in this problem. So the matrix will become 1 0 0 0 1 0 xf yf 1. Since in this problem we have done translation twice, so I will represent, or I will name it as T2, and first translation I will name it as T1. So after back translating, the figure will appear as we have placed the figure back to its original position. Means after doing back translation, the figure has been appeared in this way, which we were requiring in this transformation or in this problem. So the thing which we required we have achieved. Now we will require the total transformation, that is resultant transformation, because we have to find or we have to derive the matrices for rotation about arbitrary point. So after multiplying all these matrices, I will get direct matrices, so that I will use these matrices whenever the rotation is to be done with respect to some arbitrary point, that is xf and yf. So in the problem they will give the xf as well as yf. So now I will multiply all these matrices to find the resultant transformation. So resultant transformation TR, which is equal to, first we have done translation T1, after that we have done rotation R, after that we have done translation once again, that is back translation has been done T2. So I will write all the matrices for corresponding transformations. So it was 1 0 0 0 1 0, here it was minus xf minus yf 1. In this I will write the matrices. So I will write rotation matrix as cos theta sin theta 0 minus sin theta cos theta 0 0 0 1, and last is T2, which is just opposite to that of T1, 1 0 0 0 1 0. Here it is minus xf, so I will write here as xf because I am moving away from origin, so I am inching towards positive direction. So it will be xf here, and here it will be positive yf and 1. So after multiplying all these matrices, I will get resultant transformation, which is nothing but the rotation matrix when we have to rotate about arbitrary point xf and yf. So after multiplying all these matrices, the resultant transformation I will get as I get as resultant transformation cos theta sin theta 0 minus sin theta cos theta 0 1 minus cos theta xf plus sin theta yf minus sin theta xf plus 1 minus cos theta yf, and it is 1. So this is the matrices which will require or which we will use whenever we have to rotate our arbitrary point xf and yf. Thank you.